Hello, and welcome to interactive sound propagation for dynamic scenes using 2D wave simulation. My name is Matthew Rosen, and I'm from the DigiPen Institute of Technology, and I've collaborated with Keith Godin from Microsoft Mixed Reality and Nikunj Raghuvanshi from Microsoft Research. The motivation for this project stems from the need for immersion in interactive real-time simulations like games and VR. Immersive audio solutions have historically been relegated to using heuristic approaches that ignore some major components of how sound waves travel differently than light. To be truly immersive, we need cohesion between the two parts of interaction, with consistent audio-visual cues based on dynamic sound source and listener positions in complex environments. So the main challenge with making audio effects truly immersive is that the immersive effects require wave diffraction for complex scenes. The problem here is that robust diffraction effects require wave simulation, and wave simulation is usually too expensive to do in real time. The problem expands with the fact that modern games in VR have increasingly arbitrarily dynamic scenes. Games like Fortnite and Minecraft allow the player to make and destroy trees, buildings, and even the terrain itself on the fly. Past solutions that have diffraction have really struggled with dynamic geometry like this. Our solution aims to solve all the problems listed previously with a minimal CPU budget such that it could be viable for modern interactive applications. We run a real-time wave simulation on a single CPU core. This wave simulation generates a set of air pressure impulse responses. We restrict this wave simulation to 2D. It allows it to be run on a real-time basis, but limits it to mostly enclosed floor plans or outdoor propagation. We only simulate on snapshots of static geometry similar to past approaches, and we analyze the impulse responses generated above and parameterize them, encoding the response signals into a defined set of acoustic effect parameters mentioned earlier. The impulse responses are discarded, and parameters are used and interpolated between when rendering the audio. The last thing to note in our solution is that rather than interpolating the scene geometry during the wave solver processing, we interpolate the parametric simulation result during audio rendering. Because of the 2D nature of our simulation, we've called the solution PlaneVerb, as it operates on a plane and calculates reverberance. Here's an example of PlaneVerb operating in a game scene with a dynamic door occluding a sound source. Thank you for coming to our presentation. The source code for our project is on GitHub.